Okay, so this is wave motion lecture number 1, and we will be starting with transverse wave and try to wind it up. Transverse wave, any idea? Have you heard the name waves? Do you understand what do you mean by waves? Remember, whatever we have been doing for the previous so many classes, whether it was SHM or before it was wave optics, we are dealing with waves as such. Yes or no? No, yes. Yes, we are dealing with waves. So we'll just go through the heading, and we have seen that for energy to transfer, or light has two types of nature. One is known as a particle nature. It can be transferred in the form of a particle. Light can move as a particle, or light can move as a wave. Yes or no? Wave, whenever we talk about wave, basically what we are doing in a wave is we are transferring energy. There are two modes of energy transfer. Whether the energy is transferred from wave to wave, whether the energy is transferred from one particle to the other particle, from one part of the space to the other particle of space through a particle moving, or it can be transferred from one place to other with no transfer of particle. When the particle is transferred, this is known as particle motion. When the particle is not transferred, it is known as wave motion. So basically, we are dealing with energy transfer. We want to transfer energy from one point in space to the other point in space. If a particle is taking that energy, it is particle motion. If a wave, or there is no particle there, but still energy is traveling, then that is wave. Energy from sun comes to earth. There is no motion of particle because there is no particle there. There is all vacuum. That is wave motion. Do we understand this? Yes or no? No, yes. Okay. That is wave motion, and that is what we have been studying for quite a while now. Then these waves can be classified into two types. The first type is known as electromagnetic waves, EM waves. We will be covering EM waves just after this chapter. EM waves, or we can also call them non-mechanical waves. What are these EM waves or non-mechanical waves? They do not require any medium for their transfer. So light, all types of radiation, all these are EM waves. Since it is a EM wave, it has both electric as well as magnetic field. We have seen that in the chapter of polarization. We have seen it that in the chapter of polarization, that light is an EM wave, and we were polarizing it. It has electric field and magnetic field. We are talking about electric field. It has electric field in all the perpendicular directions, and we were trying to put it in one direction. Light is an electromagnetic wave. An electromagnetic wave has momentum. You must remember this. Uh, Electromagnetic wave medium is not required. EM waves are transverse in nature. So electric field and magnetic field are perpendicular. EM waves can be polarized. They travel with the speed of light. EM waves always travel with the speed of c. These are the important points that you must remember about EM waves. I'll give you a minute to note it down. Then we move to the next type of waves, where we require a medium to be present, and those waves are known as mechanical waves. So what are mechanical waves? It is a method of energy propagation. So energy is going from one point to the other. It moves with definite velocity. It is not the velocity of speed, because EM waves move with the velocity of speed without changing its form, is known as a mechanical wave. Energy and momentum gets transferred by the motion of particles, but the medium particle remain at their original transfer. Mass transfer does not take place. Sound is a wave. It carries energy. But here, the energy is getting transferred by the momentum of particles and the energy of particles, but the particles are not moving. So whatever particle is right in front of my mouth, that is not going to anywhere, any place else. It is only transferring in energy. This propagation is only possible if the medium has the following properties. It must have the property of inertia, remember, very important, and it must have elasticity. If these properties are not present, energy will not be transferred. If energy is not transferred, we cannot call it as a mechanical wave, because wave means transfer of energy. Do we understand this? I'll give you a minute to note it down. Let's move ahead and see what are the two types of mechanical waves that are possible. I hope you have an idea about them. The first one is the topic for today, transverse wave. What happens in a transverse wave? Remember, if the wave is traveling or propagating like this is the motion of the wave or direction of propagation of wave. The particle will move in a direction which is perpendicular to the direction of propagation of wave. Such waves are known as transverse wave. The particles of the medium oscillate in a direction perpendicular to the direction of the wave. Vibration on a string, wave produced in water on the any surface or solid. If I put a stone in water, whatever waves are created, you can call it transverse wave. In a transverse wave, we have crest and trough. You must remember what is a crest and what is a trough. We remember this. If this is a wave, it moves like this. The topmost portion on the positive side is known as a crest. The bottommost portion on the negative side is known as a trough. We know this, yes or no? Can I have some raised hands? So these waves travel or propagate by the phenomena of crest and trough. I hope you have noted it down. This is all about transverse wave. We will be dealing with them in details in this chapter, but let us first go through the basic definition so that we understand that what are transverse wave. Remember, in transverse wave, if you look at the last line, in transverse wave, the particles are oscillating in a direction perpendicular. Hence, it is possible for them to be polarized. Do you see that? It is possible for these. It is possible for these waves to be polarized, as I can highlight it here. Polarization of transverse waves is possible because the direction of propagation is perpendicular, but it is not possible for longitudinal waves. Why it is not possible for longitudinal waves? Because when we see longitudinal waves, we will see that in this type of waves, their particles of the medium do not oscillate perpendicularly, but they oscillate in the same direction as the direction of wave propagation. They oscillate in the same direction as the propagation of wave. Sound wave is a best example, and the waves in gases are best example for longitudinal waves. If the wave is moving like this, particles are also oscillating like this. Particles are not oscillating like this. So in transverse wave, we have crest and trough. In longitudinal wave, we have compression and rarefaction. What is the compression and what is the rarefaction? In compression, the particles are much closer, are very close. In rarefaction, the particles are far away. So at places of compression, the pressure and densities are maximum, whereas at the places of rarefaction, they are minimum. So particles in the case of compression are very tightly packed. The pressure is very high, the density is very high, but in case of rarefaction, the density and pressure are minimum. Do we understand this? Yes or no? I'll give you. Then we move on to the next heading, which is the equation of a progressive wave. Now this wave can move in positive x-axis. This wave can move in negative axis, and this is how the formula looks like. Y is equal to a sine omega is out, t minus x by v. Now this formula is somewhat different to the formula in simple harmonic motion. The only difference is in simple harmonic motion, if I just write the formula here and I'm going to write the formula here. In simple harmonic motion, we had seen that the formula was y is equal to a sine omega t. Do we remember this? Yes or no? But remember, in simple harmonic motion, when we were dealing with simple harmonic motion just in the last class, we were dealing with only one particle. So it was the motion of only one particle, and therefore the formula was looking so simple. Y is equal to a sine omega t. But here you must understand that when the wave is moving, not only one particle, but all the particles of the medium are moving. Do we understand this? So this equation which I see over here, this is not the equation of just one particle. It is the combined equation of all the particles put together. So what you see here are two terms that you must put. There are two values that you must put. One is the value of t at what time, and one is the value of x. Which particle are you talking about? There are an infinite number of particles on the wave. T tells us, T gives us the time, at what time you want the position. X tells us where is the actual, where is the particle located, what is the x coordinate, and therefore y is equal to a sine omega t minus x by v becomes equation of a wave in positive x-axis. In negative x-axis, minus sign gets replaced by plus sign. So the equation becomes a sine omega outside t plus x by v. Here t stands for time. At what time? X stands for the x coordinate of point P, and v stands for the speed of the wave. At what speed the wave is moving. Do we understand this? Yes or no? Can I have some raise hand from all of you? I'll give you a minute to note it down. Well done. Then we move on to some important points. Whatever equation we have written, equation number 1 and 2, it gives the displacement of particle from equilibrium at any time t. It means y is the displacement of point q from the mean position. This point q is at a distance x from the origin. Periodic motion of point 2 can be represented by y is equal to a sine omega t. So once you know the position of point, we can use the simple equation y is equal to a sine omega t. Remember, y is equal to a sine omega t. It is the equation of one particle, but wave is the equation of all the particles, and therefore we have omega t minus x by v if it is moving in positive x-axis. If it is moving in negative x-axis, it is x plus, t plus x by v. Do we understand this? If you want to find want to find the velocity of any particle, you differentiate the first equation or the second equation. If you want the wave velocity, you find out dx by dt. Normally, wave velocity is given to you. Do we understand this? Since this wave is moving in the forward direction, if it is minus x by v, it will be moving in the reverse direction if it is plus x by v. This is known as the equation of a progressive moving wave. We'll also understand standing wave. This one is a moving wave. Do we understand this? Yes or no? Can I have some raise hands? I'll give you 2 minutes to note it down. Let us now move ahead and see some important terms that will come in wave equation. Remember, most of those terms are already known to us. A stands for amplitude, which is the maximum displacement of a particle from its mean position. Periodic time is the time taken to complete one oscillation. Number of oscillation in 1 second is known as frequency. Do we understand this? Yes or no? Wave frequency or frequency is the number of oscillation in 1 second. Omega is 2 pi by 2 pi n or 2 pi f, or it is 2 pi by t. Do we understand this? Yes or no? We have already seen it many times in simple harmonic motion. So we can just move ahead. I have also told you the value of wavelength. Wavelength is the distance between two particles in the same phase. This is a crest. This is also a crest. If I find the distance between the two crests, that will be wavelength. Or it is the distance traveled by the wave in one time period. This is a trough. This is a trough. The distance between two troughs can also be known as the wavelength. Do we understand this? Yes or no? So there are two ways in which you can write the wavelength of a wave. It is the distance between two consecutive particles in the same phase, two troughs or two crests, or you can write it as distance traveled by the wave in time capital T seconds, where capital T is the time period. Do we understand this? You must also remember the relation between V, N and lambda, or V is equal to F lambda. We have undergone, we have seen this relation many a times. I hope you remember them. Well, in this particular chapter on wave motion, the only thing you have to understand is these three formulae, and if you can remember these three formulae, you would be doing very nicely. So please note down these formulae very, very carefully. V is equal to N lambda. This is the or F lambda. This is the formula that we already know. F is lambda. F is 1 by T, so it becomes lambda by T. Time period is 2 pi by omega, so it becomes omega by 2 pi into lambda. You can write it as omega by k, where k becomes 2 pi by lambda. This k is known as your wave number. If you can remember this small thing that is right now on your screen, almost all of your wave question will be coming from this equation. So I'll give you time, a minute, to note it down in your copies. Well then, these are the next terms that are going to come. Very important terms. Question are going to come on these three things. So please remember intensity. What is intensity? Energy which is falling per unit area, per unit time is known as intensity, and this is the formula for intensity. No one is going to ask this entire formula, but what they are going to ask is what all factors intensity depends on. It depends on density, it depends on wave velocity, it depends on wave frequency. But the most important factor here on which question come is what is the relation of intensity with amplitude. Remember, intensity we have already seen is proportional to amplitude square. Remember that wave optics wala chapter? Yes or no? No, yes. This is the original formula. If you can remember this original formula, nothing like it. 2 pi square f square a square rho v. So it is directly proportional to f ka square, directly proportional to amplitude ka square, directly proportional to density, and directly proportional to the wave velocity. Energy density is the next thing. It is the energy per unit volume is known as energy density. So you can find it out by energy ka intensity divided by velocity. So the formula of energy density is same as the intensity of the wave, but it is just divided by the velocity. So velocity does not come. Wave pressure, whenever a wave is hitting a surface, it is going to exert some pressure. That pressure is known as wave pressure. Please mark this thing down. If you remember the formula of intensity, just divide intensity by velocity. You will get the formula of energy density. I'll give you a minute to note it down. We move ahead and see the different forms of equation of wave. There are 5, 6, 7, 8, 9, 10 different forms in which you can write this wave equation. This is form number 1 in which I remember it, omega t minus kx. Then you can put the value of k as 2 pi by lambda, and you can have different ways in which you can write this formula is wrong. I think there are different ways in which you can write this. Do we understand this? So these are the different ways in which it is written. What they have done, is you can just take out. There are different ways in which it is written. You can remember way number 1. You can remember way number 2. You can remember wave number 4. This is the correct array. This one is wrong, so I'll just take it off. Then I will give you a choice of how many different ways you can remember it. If you can remember it, way number 1, way number 6, and way number 8, I think that will cover almost all types of questions that are going to come. This is the displacement of a particle at different time at a fixed x. The value of x is fixed. This is the formula. This is the graph for a fixed particle. This is the formula. This is the graph for the wave at a fixed time. This is the equation or form of wave at time t. The previous graph is the graph of one particle at all times. The second graph is the graph of all particles at one time. This is one particle at all times. How the particle will move. One particle at all times ka graph. This is all particles at one time. Do we understand the difference between the two graphs? Yes or no? No or yes? In graph number 2, I am showing you where all the particles are at one given point. In diagram number 1, I am showing one particle at all times. Do we understand this? Can I have some raised hands? I'll give you time to note this down. Formula number 1, formula number 6, formula number 8, and the two graphs. Well, then we move ahead and write the next heading, and this next heading we have already seen. Interference and superposition. What is superposition? If in the same medium more than one wave are traveling, then the resultant displacement will be given by y1 plus y2 plus y3 and so on. On what all factors this resultant intensity depend on? It depends on the amplitude, it depends on the frequency, it depends on the phase difference, and it depends on the direction of motion. We have also seen that if the frequency is same and amplitudes are nearly equal, and if they are moving in the same direction with a constant phase difference, once they superpose, at some point the intensity is maximum, at some point the intensity is minimum. That is known as the phenomena of interference. Do we remember interference? Yes or no? I think we all know this, so I can move ahead from this. Yes or no? Interference. Can I have some raised hand that we remember this? Well, this is interference. When waves of equal frequency and nearly same amplitude moving in the same direction, they superpose, then interference occurs. Right now, the equation is looking at somewhat different. This is wave number 1, and this is wave number 2. Remember, the formula of amplitude remains same. Amplitude square is a square plus b square. A1 square plus A2 square plus 2 times A1 A2 cos phi, where phi is the phase difference, and intensity का formula becomes I1 plus I2 plus 2 times root over I1 I2 cos phi. Cos phi is the phase difference, and how do you find the phase difference? I have already told you the formula. This is the phase of particle 1, this is the phase of particle 2, this is phi 2. Phi 2 is used here. You can call this is delta 2, this is delta 1. When I subtract delta 1 from delta 2, you will have the value of phi. Do we understand this? Yes or no? I'll give you a minute to note it down. The next heading is types of interference. It is constructive interference and destructive interference. We have seen for constructive interference, part difference is n lambda and phase difference is 2n pi. Intensity maximum is A1 plus A2 का whole square. Intensity minimum is A1 minus A2 का whole square. For destructive interference, part difference is n minus or n plus half lambda, and phase difference is 2n minus 1 or 2n plus 1 pi. Do we remember this? Yes or no? Please let me know. Yes. So we move on to the last part of this today's class. And last part of today's class consists of reflection and transmission of waves. Now, how does wave reflect or get transmitted from one medium to the other medium? Remember, if the wave is moving like this and it is getting reversed, it can get reversed like this. So you can see here a crest is reversed as a trough. So it undergoes a phase difference of pi. So that is one thing that can happen. It can undergo a phase difference of pi. This is the blue case. In the red case, you are seeing a crest after reflection being reflected back as crest. So the phase difference between the two waves, the incident wave, this is the incident wave, and this is the reflected wave. In red case, there is no difference. In the blue case, there is a difference of pi. Do we see this? Oh, yes or no? Then how do we find out whether a wave is reflected, whether it is inverted or it is not inverted? The concept is given here. The concept is given here. So please underline reflection with inversion and reflection without inversion. So what is the funda? If a wave enters a region where wave velocity is smaller, the reflected ray is inverted. If it is getting reflected from a medium where the wave velocity is smaller, that means it is getting reflected from a denser medium. When it is getting reflected from a denser medium, the wave gets inverted. Will you remember this? When the medium is denser, I'm moving from rarer medium to denser medium, the wave would be inverted. If the wave is moving from, if the wave enters a region where the wave velocity is larger, the reflected wave is not inverted. That means when it is reflected from a rarer medium, it will not be inverted. Do we understand this? The third case is pretty damn simple. The third case is pretty damn simple. The transmitted wave is never inverted. Can you remember the three cases here? If the wave is reflected from a denser medium, it is inverted. If it is reflected from a rarer medium, it is not inverted. If it is reflected from when it is transmitted, it is not inverted at all. That finishes our today's class. For transverse wave, what we have seen is the equation of the transverse wave, a progressive wave, omega t, omega common, t minus x by v. V is the speed of the wave. We have seen interference. We have also seen reflection. In the next class, we will move ahead and try to wind up this topic of transverse wave. I would request you to go through the lecture once again and read the notes carefully so that we can move faster in the next class. Take care and have a nice day. If you have any problems, do ask me.